In this lesson, we shall focus on applied mathematics, APM 3711. We shall be looking at numerical methods 2, applications of the methods to a wide range of problems. We need to first recap on the following method, which is at the heart of all the operations. The notion of what we call the Euler method, what we call the simple Euler. Okay, we've learned Taylor, and we've spent time on Taylor. We've done a wide range of problems, but need to understand that Taylor of order 1 is called the simple Euler. We have used the simple Euler when doing the shooting method. Right, we dealt with the shooting method, but the shooting method we studied applies what we call the simple Euler, and therefore this simple Euler is actually so significant to the extent that pretty much every exam question will have this simple Euler method, and use the simple Euler for the differential equation with h equals 0.2, for example. And what do we need to get? If this is a differential equation, dy dx, which is x over y at 0 equals 1, to get y at 1, compare your numerical solution with the analytical solution. Y squared equals 1 plus x squared. Okay, so I want us to recap on this because we shall be using it in many aspects of the course. Pretty much most of the methods we have, like the Adams Bashforth method we did, the Adams three-step Bashforth method we did, makes use of the simple Euler as well. And obviously, I mean, other methods as well, like your Runge-Kutta of order 2 has found a lot of applications as well. But I want us to just recap on this method, which is a very, very exciting method. So we note that for the simple Euler method, there are a couple of things that we need to learn. Okay, when need arises, we shall use the octave, because the octave algorithm is used to find solutions to systems. Whenever we have systems, we shall use octave, because the octave is used to solve systems that arise from these systems of equations. So for the simple Euler method, the algorithm, for instance, you need to just remember the algorithm. What is the algorithm? Right, so the algorithm is a yn plus 1, which is always y sub n plus h, f of x n y n. F of x n y n plus h y prime of this, where x0. Right, so we actually obviously ponder on this, but we're looking at the fact that y0 is 1, which is the initial value. So which means, therefore, that x0 is the 0. And our y0 is actually y at 0, and y at 0 is 1. And whenever we have fxy, it is x out of y, which is that. Okay, obviously we note that in the whole course here, whenever we have dy dx, it is f of x and y. And as we continue with our discussions on the simple Euler, what does the simple Euler mean? This is what we need to remember. So the simple Euler is exactly this here. It's exactly this here. This formula here is what we call the simple Euler, this formula. It's what you call the simple Euler. Y sub n plus 1. We use this when we do the shooting method, but also we use it when we are just studying the simple Euler by itself, as an art in itself. This is the formula. So we use it to solve problems. But, right, in the way we use it, we will arrange the calculations in the form of a table. Okay, we'll arrange the calculation in the form of a table, obviously with columns for x sub n, y sub n for examination purposes, the prime, and yn primed. And as we continue, we note that the table we shall use will be filled. Okay, this method is very important because in the shooting method we use it. So you need to understand it well. One row, for example, at the time we use x sub n and y sub n to find yn primed, which equals fxn y sub n. And then in the process, okay, we note that obviously this we also call, so there are two names for this. We need to note that the first name is that yn primed is what we call the dy dx, but it is also called f of x n y sub n. Right. When this is the case, then multiply by h to get h1 yn primed and add these to y sub n to get yn plus, and we're just describing the algorithm here as we shall execute it for the next row. As said already, now the octave, its applications in this course, it's very limited, just used to solve systems, but we shall illustrate how that will be done. Okay. Let us construct a table here. Let us learn how to construct a table for, so we're going to look first at the h equals 0.2, but we're also going to look at y sub n, which is fxnyn. Dx. So now we continue. We draw this table like this. And we'll have x sub n. Let me see if I launch the calculator here, so that I can know. I'm trying to see if the calculator has been launched. Okay. Yeah, okay, I need to get there. Okay, I'm going to launch the calculator now because just so that we practice. Going to launch our calculator so that we practice. Right, I'm going to launch the calculator so that we practice. Here's the calculator. Right, here's the calculator. Right, so we're just practicing with this simple Euler right now for a start. Just a warm-up exercise. As we're trying to see what we can do. Right. Okay, let's practice with this. Now we're gonna start by looking at how we draw the table in the case of the simple Euler. Where the need arises, we shall solve the systems that will arise using Octave or MATLAB. Okay, shall use Octave or MATLAB where the need arises, where we have a system we need to solve and so on, and we can use the Octave to do it. Okay, right. So now if this is 2, 4, 6. Okay, we're drawing these things here. We're drawing these things here. We're drawing a table. And then with this table, we're gonna fill in the table, like we're gonna have 0.0. Okay, because now our h is 0.2. We're just reminding each other this method, but our h is 0.2, and we start with x0 equals 0, y0 is 1, x0 is 0. Okay, we're calling it 0.0. And then we add 0.2 to it. 0.0 plus 0.2, we get 0.2. But if we add 0.2, we get a 0.4. If we add another 0.2, we get a 0.6. Right, and then if we add a 0.2, we get a 0.8. Okay. Which is a 1.0. 1.0. 0.8. Right, so y sub n. Okay, now if you're dealing with y sub n, then we're going to have the fact that the axes have already been put, the xn have already been put, and then we are putting the yn's now. And to put the yn's, we actually will proceed as follows. Like we start with the first one, y0 is 1. Y0 is 1, so you're going to have a 1 here, a 1.0. And then our biggest machinery is actually, deployed right now. Find that. So we remember that we have had this here. Right, we have had this a simple Euler, yn. To get the next value, we use yn plus 1 equals yn plus h, that. Okay, so that's what we're going to use. Yn plus 1 is yn. yn. Right, so you continue. Okay, we have our y0 is 1. Then we need to also calculate a y1. So using this formula, would know that a y1 would be y0 plus hfx0y0. Okay, this is fx0y0. Okay, can I use a calculator most of the times in this problem? So now, if this is the case, if fx0 is this, the derivative, so we're gonna use, for instance, if we want to get x, if we have x0 divided by y0, what is x0? X0 is 0, but y0 is 1. 0 over 1 is 0. So f of this would be 0. And then this would be the same as our y0. Y1 will be y0, and our y0 is still a 1. But we'll just put a 0.0. Dealing with a 0.4. 0.4. Right. Okay, now 0.4 is the next one. So this is why this is like n0 for x0, then there is n1, there is n2, there is n3, there is n4, there is n5. Okay, let's practice with this. So now, if we continue with our analysis of this problem, we have a, what is it? Now, for n equals 2, we have 0.4, which is our y2. So y2, according to this formula, so we can see that our y2 is going to be what according to this? Okay, when n is 2, it's y2. Then but it's going to be y1 plus hfx1 y1. So now at this point, we recap on the simple Euler and its applications. Well, the table, we can still do without the table, but the table organizes our work. So normally we can even use the table in the exam. Right, because it's a standard procedure for this particular problem here. Okay, now we are dealing with n2, and therefore y2 is y1 plus h. But what is f of x1, y1? It's x1 divided by y1. What is x1? What is x1? Right, so which means that we have x1 over y1 according to this, because it's the f is x over y. So what is x1? X1 is 1. What is y1? Right. X1 is 0.2, that is. X1, because it's x0, x1. X1 is 0.2 divided by 1, which would be 0.2 divided by 1, which is 0.2. 0.2. 0.2. Okay. So we have that this f is 0.2, but h is 0.2, y1 is 1. Let's use a calculator. So we will keep track of the things here. Okay. Let us just practice with this and see what we're getting. A simple Euler. So now we have y2, which is y1. Y1, this is y0, y1. Y1 is 1. So you punch a 1 here. Okay. Okay, so now you have This is x1, y1. What is x1? X1 is 0.2, so you punch a 0.2 here. And then the y1 is a 1. Which is 1.04. 1.04. So here you're going to put 1.04. Okay, we're just finding these values. So let us continue and find more of this. So now we're going to find, for instance, our next y. So this is y at 0, which is y0, y1, y2. Then we're finding y3. You're finding y3. Right. So y3 is going to be, according to this, yeah? y3 is y2. Right. So y3 is y2. Okay, this is y0, y1, y2. Not 0.2. And then now we want to do fraction because it's x over y. Then we want to do, because it's at n equals 3, so it's y3. If it is y3, then it's going to have what? Okay, so obviously need to organize that. So it's going to have the previous. It will have the previous. Because y3 is going to have y3 is going to have y2. H f x2 y2. Right, so this is our y2. And then here we have x2, which is 0.4. And then y2 is 1.04. Like this. Let's check. This answer is 1.1169230077. So we punch, we're going to write this one here, which is 1.1169230077. So we continue with the next one. Let's look at the next one. Okay, so now the next one is at n equals 4. I'm going to punch that. Okay, if you look at it at n equals 4, at n equals 4. Okay, so at n equals 4, you're dealing with, this would be at n equals 3, y0, y1, y0, y1, y2, y3, y4. y4. Okay. Right, so now if this is y0, y1, y2, y3, y4, let us deal with y4. So y4, if we want to get it, we're going to use y3, the previous. So we do that. So it's 1 point, according to this, is y3, so it's 1.1169230077. That is y3 plus h is 0.2, okay, because the formula is hf times the previous x over y, the previous x over y. So we're going to do x over y, 0.6. Not 0.6. 69 23 077. Check this one out. 1.224361094. 1.2243 61094. That's what we have. 1.2243 61094. Okay. Next. We do one at 0. We do the next one at 0. Okay. So now if we want to find at 5, y5. Y5 would be y4 plus h, f, x4, y4. All right. Should be y4. 1.2243. One point two two four three six one zero nine four. Not 0.2. And then you want to do x over y. Not 0.8 divided by 1.2243 61094. 1.355 041496. 1.355 041496. Okay. So we found all the y's, and then now we need to find the y primes. All right, so we need to find the y primes. So now the y primes are found as follows. So if this is the y primed, as we said already, so this is the yn primed. So the yn primed is a dy dx. Is a dy dx. The yn primed becomes a dy dx. Okay. Now, if this is the yn primed, what we then do, we perform division. We perform division. Right, so the way we do it, we perform division. Okay, so which is the yn primed, which is xn over yn. Right, so if we perform the division, let us continue with the division. So now we're going to say, if this is what we regard as the prime, the derivative. So now we're going to have, according to this, is x over y. So we have 0 divided 0.0 divided by 1.0. It's just 0. So write 0.0. 0.2 divided by 1, 0.2. 0.4. So now, not 0.4 divided by 1.04. So that would be 0.38461. Right, we continue. Just 1 minute. Hello? Hello? Wrong number. Right, so we continue. So this is going to be exactly the following. Okay, yeah, because we got 0.3846153846. You see, that corresponds to what? Well, it does correspond to the division. Then the result that should come here. So this is y0 primed, y1 primed, y2 primed. So y2 primed is x2 over y2. Okay, so if you do x2 over y2, then you get to 0.38. Not 0.38. We got 0.3846. 384. Okay, that is what surely we're able to get on the calculator. As said in the exam, by and large, the most useful tool becomes a calculator for this than any program that you can wish to run. The calculator will be the fastest way to do most of these problems, I can promise you, than any algorithm you can always get on Octave or whatever. Octave itself has limited applications with MATLAB there, but obviously we shall use it whenever the need arises. So we continue with our investigation. Okay, now we're getting, this is y0, y1, y2, then y3. y3 primed. So y3 primed is going to be x3 over y3. So x3 over y3, 0.6 divided by this. Right, so you continue. Not 0.6 divided by 1.11 69 23077, which is 0.53719000826. Right, 0.53719000826. 0.53719000826. Right now, we're going to find this one. Y0, Y1, Y2, Y3, Y4 primed. So now, this is X3, Y4. To get this. So X3 itself, it's going to become what? Let us use a calculator. So it's going to be 0.8. Okay, because divide X by Y. The Y is 1 0.2243 610 94. Okay, it's 0.65340201. 0.65340201. 02. 0.65 34 0201. So now HYN primed. HYN primed. Now you take the H, which is 0.2, you multiply by the prime. So 0.2 by 0 is 0.0. 0.2 by 0.2. Right, so do 0.2 by 0.2. So if we're going to do 0.2 by 0.2, you get 0.04. 0.04. Then you do 0.2 times this, 0.2 times this, 0.2 times that. So for example, if you do 0.2 times 0.38, 46, 15, 384. Okay, we're getting 0.076, 92, 30768. So that's what we're putting here. So it's 0.076. Nine two. Yeah, 0.076923076. So now we continue, then we plug in more on the simple Euler method. Yeah, all right. So now, for example, if you have, we actually now need to get this one corresponding to this. So you're going to multiply our H equals 0.2 by the Y primed, and we plug in the value there. So we multiply 0.2 by the Y primed value. So let's multiply this one. Not 0.2 times 0.53 71 900 826. Okay, which is 0.10 74380 Yeah, 0.10. I just pressed whatever. Okay, I lost the value. Right, so if you multiply, okay, multiply the 0.2 H with the Y prime. So as indicated, that is 0.2 by the 0.53 71 900 826, which is 0.1074380 0.1074 38016. Okay, then you multiply again the 0.2 with that. Okay, so we have 0.2 multiplied by 0.65 340 201, which is 0.10 0.13068 0402. That's what we have. So we have here 0.1306 0402. So obviously we're doing this to get y at 1. To get y at 1. Right, to get exactly y at 1. So then obviously in the end we can see that y at 1 is exactly that value there. It is exactly that value there. So looking at this table, we are able to see a couple of things. That the way obviously this table is structured, it allows us to use the fact that yn plus 1 is yn plus h yn primed. Yn primed. Right, so that is what we have. That is what we have. That is what we have. So in other words, to get the y values, a student would have just got the y primed, the h, yn primed, and therefore if you add this with that, we can work it that way. So when you get this with that, when you add them up, they give you this. You add this with that, they give you this. You add this with that, they certainly give you that. So that would be the way. That is, you add yn. If you add yn, what we're saying is you add yn together with hyn primed. If you add yn together with hyn primed, you'd get what? Right, so you add yn with hyn primed, you'd get the next yn plus 1. You get the next y value. Right, you'd get exactly the next y value. Because when you add 1 with 0, you get 1. Right, so you add these with these, you get that. 1 plus 1.04, you get 1.04, and so on and so forth. The objective of the table, obviously, is to get the value of y at 1. So we got that y at 1 is this. So in other words, it is actually very enough to then come and then say y at 1 is 1.355 041496. 1496. 1496. Okay, we continue with our analysis. We actually continue with our analysis. Okay, I want us to recall the question and what the question obviously expects us to do here. So now, as said already, much work will be done using calculator in this case than octave algorithms. Now we need to compare your numerical solution with the analytical solution. So we have got a numerical solution. So in other words, from this, we have got that y at 1 is approximate. You can use an approximate symbol. Can use an approximate symbol there. So it's approximately this 1.35041496. 1.355 041 496. Right, so this is what we have. But you'd have exactly the following. Okay, yeah, we want to compare with the analytical solution. Right, so the analytical solution actually is the following, which is y squared is 1 plus x squared. One plus x squared. Right, so okay, why do we use a plus sign here? Because somebody will be like, okay, there are two solutions, but we're gonna only use only y equals the plus square root. Why only the plus square root? Right, we're only using the plus square root because what we are seeing here is clearly that y at 0 is a positive number. Okay, because now obviously if you do, this is y at x is this. So when you're doing y at 0, so you'd have 1 plus 0, which is plus or minus 1. So okay, you have y at 0 is plus or minus 1. Okay, yeah, but we're saying therefore that our y at 0 is only 1. What are we saying here? So y at 0 is only 1, so we are then saying we're going to only use the positive. The positive. Okay. Okay, using the positive, I want us to analyze what this is. So we then say at x equals to 1, because we want to get y at 1. So we're going to get y at 1 because this thing here is y at x. 1 plus 1 squared, which is the square root of 2. 1.414 21 35 62. Okay, wide 1 is square root of 2, 1.41 for 213562. Okay, so that's what we have. So now, if we are then saying y at 1 is exactly the square root of 2, but it is approximately 1.414 213562. Okay, this one is exact. Okay, because we used the analytical solution for it, and the analytical solution is accurate. Okay, it is the solution to this differential equation, but it is therefore exact, this analytical, the solution from the analytical solution, yeah? Or the square root of 2 is accurate, but it is approximated as 1.41, etc. Okay. This one here is approximate. Is approximate. It is approximate. It is approximate. Right, so being approximate as it is, okay, we can see we've put these two values side by side. But you see, putting these two values side by side shows that the simple Euler method is far from being accurate, because the accurate answer is 1.41 for 213562. That is accurate. Obviously, this is the exact answer. Square root of 2 is the most exact. Okay, but approximated is, but the wide one, according to the simple Euler. Now we're just using the approximation in the exam. They normally say use the simple Euler, or they say use Euler. There are two methods by Euler. So there's what we call the Euler method, which you also call the simple Euler. And then last time we used the modified Euler. Also used the modified Euler method. Okay, we also use the modified Euler method. However, then the simple Euler is what we're discussing now. Last time we used the modified Euler. So we must be aware of the modified Euler also. The modified Euler we used last time had two corrections. You can do two corrections, you can do one correction. Okay, so sometimes they bring the question about that. Okay, yeah, they bring a question about either any of this. Okay, let us continue now and practice for mastery. For mastery. Right, okay, I want us to also calculate the error. There's an error. What is the error? So now let us discuss the notion of the exact solution. What is the exact solution? Okay, the exact solution is the square root of 2, but it's 1.414 213,562. And this is the square root of 2. Let's check. $1.41,562. Then you'll also do the error. Then you'd have the Euler. Then you'd have the Euler with H equals 0.2. And then we were able to get the Euler, and then it became 1.355041496. Okay, that is what we got. This one, 1.355041496. That's what we got. Then what was the error? What was the error? Okay, we're just learning how to compute the error. So the error is therefore the difference between the two, and then we can be able to get the percentage error. Let's first get the error. So to get the error between the exact and the one which is the approximate, so we're gonna do, for example, so the exact one, you can see it's bigger because it's 1.4, but the Euler's method gave us a 1.3, which is smaller. So now we're going to take the 1.4. You can take the square root of 2 to be more accurate. Because obviously this is like an irrational number. So, but we subtract 1.355, not 4, 1496. And the result. So now what we're then getting is that we have exactly this, which is 0.05, right, which is 0.05, that up to, yeah, 0.05917206637. Right, so you can have that. So that is the error. The error is 0.05 917 2066 2066 2066. So now let's continue. H is 0.1. Okay, now we're going to practice with this one. There's a bit more values. The simple Euler, this is a mastery problem, a mastery class on the Euler method. Okay, we should also call the simple Euler. So we're going to do this method. So we're going to do 0.0. And we do the next one, which is 0.1. 0.2, 0.3, 0.4, 0.5. Yeah, we're going to do this one in 2 stages. Then you're going to do also xn, 0.6, just more practice, 0.7. Okay, because we must get to 1. 1. So we have 0.7, then we have 0.8. Okay, yeah, because see the way we are doing it, we're doing it like this because of this, the step size is so small. It's 0.1, 0.1, yeah. H is 0.1, so it's so small. 0.9, 1.0. So we continue. We continue. We continue. So we continue. It should be 1.0. Yeah, because y0, then it's 1. Y0, this is x0 is 0, then y0 is 1. Okay, but now we're just using a different step size. That's all. Right, so you can be able to run through this table quickly. As we note the patterns here. So here we're going to put yn. Hyn primed. So we continue. Okay, let's continue, please. Sorry. Let's continue and solve this problem. Okay, we have yn primed, hyn primed. For example, if we are to go through this table in a way that will make life very easy, okay, we start with x0, which is this, and then y0 is 1. You can write it as 1.0 to 2 decimals, and now, or to 1 decimal place. Right, so now we then say yn primed. So this would be yn primed. Yeah, yn primed. Yn primed. So if this becomes like yn primed, let us see what we can do. Okay, yn primed, so we have xn over yn, giving us 0.0. And then now we're going to have this one, which is, we multiply this by 0.2 because, yeah, by 0.1. So h is 0.1, multiply h by yn primed, 0.1 by this is 0.1, is 0.0. 0.0. So we have 0.1, which is xn, and then to get the next y, we remember our formula. Yn plus 1 is, this is a master discussion on this simple Euler. Okay, this is the formula we use for what we call the simple Euler or just the Euler method. Now, obviously, we just need to master this because it finds applications in the shooting method, which you must know for exam purposes, etc. Now, if you look at the xn, right, you'd have exactly the following. Right. Good. Okay, we continue, please, with our analysis of this. We're just focusing on the right. We're focusing on the things we need. Focusing on the things we need. Okay, we're practicing just what the simplest way to deal with this problem is, and how best we can quickly finish. And I think that is the strategy to beat the clock when it comes to this. It's 2 hours, and I feel it should be more. Right. Provided the lecturer promise to increase the time. I'll have to check that because I I saw your communication there. I feel that this module is supposed to be like 3 hours, you know, but, or even 4 hours. But now they made every exam 2 hours. And now if you got your calculator, the time is gone. You got your calculator up, you punch, and this, by the time you check, time is gone. So because of the calculator work and the computer programs you might have to run, the truth is it was supposed to be given extra more time than it is given, but it's not the case. So right, so my point therefore is we need to have a strategy to beat the clock. When you're doing like the simple Euler method, how do you beat the clock? All right, we've filled in the table there so far, and then now let's deal with this. Is like we said, n equals 0, n equals 1, n equals 2, right? N equals 3, n equals 4, n equals 5. N equals 5. So now, if we have this, then we're going to get to the yn. Yn. Okay, we're practicing. This is actually exactly y0, which is 1. And then we need to get y1. We need to get y1. So the easiest way to get y1 is to say y1 is y0, h, x0, y0. So then in the end, you have y0 plus h. So this one is the same as, you can write it as yn plus 1 is yn plus h, yn primed. Yn prime. So now you add this with this. If you add hyn and yn, you get the next y value. The next y value. So now we have 0, 0. We add to 1. 0.0 plus 1 is 1.0. 1.0. Okay, it is exactly 1.0. Then now you need to get yn primed. Yn primed is xn over yn. So xn is 0.1 divided by this. 0.1 divided by 1 is 0.1. You multiply. Which is 0.01. We continue. Okay, y'all. Let's get this one. So to get this one, which is the next y, what do? We take yn and h, yn primed. So we take this one plus h of that. So 1.0 plus 0.01, you get 1.01. Right, and you get that 1.01. Let's complete the table here. Right. So just one strategy to get to be able to do the Euler method in a slightly organized manner where the table is being used. Right. And once again, just for practice purposes and for procedural fluency. Okay, now to get the y primed, it is x over y. Right, so you do x, which is 0.2, and then y, which is exactly that. Let's use a calculator for this one. The x is 0.2. The y is 1.01. Divided by 1.01, and then you get the answer. 0.198, blah, blah, blah. 0.198019802. 0.198019802. So we continue. We continue. Now, at this point, okay, so now we multiply h by this one. But h is 0.1, so just multiply. Not 0.1 times 0.198. 0198 02 0.0198019802. So, yeah, that's what we've got. Just confirming that we've got the correct answer. Yeah, 0.01, etc., etc. Yeah. So that's what I'm going to put here. 0.0198 01 9802. Okay, now to get the next y, you add the previous. So you're gonna add this one, yn, and the hyn primed. Yeah. So you add this one together with this, then you shall get the one that is gonna be there. So in other words, you're getting for n equals 2, you're adding a y2 plus hy2 primed, then you get a y3. You get a y3. You're adding that. 0.0198 019802. Okay, then we have 1.029. 1.029, then 801,198. Right, so this one gonna correspond with this. 1.02980198. And then now you get the prime. The prime is x over y. So you're gonna actually have x over y, meaning you have 0.3 divided by that. Okay, so let's check. Not 0.3 divided by 1.029 80198. 1.0291. Yar. Check this out. So for the yar, it's 0.291 131 181 425. 0.291 31 8142. And then I'll just multiply this one by 0.1. By 0.1. So if you multiply by 0.1, what happens? The decimal point shifts. Okay, yeah, there's a shift the decimal point because this 0.1 is like dividing this number by 10. Like divided this number by 10, then it becomes 0.01. Okay, so we continue with our investigation here. Right, we continue with our investigation here. Continue with our investigation. Yeah, it's just to calculate work. So we're going to take this one and multiply by 0.1, and then we get the next answer, which is 0.29 131 8142. 0.029. So we have 0.029 131 8142. Okay. All right. So we have 0.029 131 8142. Then we have n equals 4. N equals 4. And then we have 0.4. So to get this value here, to get a yn plus 1, need a yn plus h yn primed. In view of the notation used in this module, so you're going to take your yn and then you add to this last one, and you get the value that we're going to put here. So that means that we're going to do the following. Right, so we're going to do 1.02 9 80 198 plus, okay, then you add this one, 913 18 142. Right, so the answer is 1.058933794. Right, so that is going to be the value that is going to correspond to the value we're going to put here. So it's 1.058 933 794. Okay, this is procedural fluency when it comes to the simple Euler. Okay, so now we get to the next value. To get this value of the prime, you divide x by y. So dividing 0.4 by this, you're going to get the value that we're going to put here. Okay, it depends on how you organize your things, because in the end, what do we want? What do we want to achieve? We want to get a y at 1. That is what we want to achieve. So now we're going to multiply, for instance, it's x of a y. So you're going to do x of y. What is x here? It's 0.4. 0.4 divided by 1.058. 933,794. Right, so continue. We continue. We continue. 0.3778 that. 0.3777 3844. Then multiply by 0.1. Okay, this is numerical methods for you. Just repeating the steps until you get the answer. So now you have this one, you multiply by 0.1, because multiply h by the y primed. H is 0.1. Then you get 0.03777384406. Right, good. So this is the value we're going to put here. 0.03 777 3844. Right. So now you have x divided by, okay, yeah, we're adding now. So now to get the value that must be put here, we must add this and that to get the value that must be put here. So if we add the map, okay, this is just a simple Euler. It should not be something bizarre to say, what are we doing here? To 1.0589 33794. You add the last one in the block, which is exactly this one here. 0.03 777 3844, which is 1.096. 1.096. Right, 1.096707638. 1.096 707 638. Right, so we continue. Then we have the y primed, which divides x into y. Which divides the x and the y, which means 0.5 divided by 1.09670 0.4638. 0.45591000189. Right, so this is it. This is it. So we're going to get the value and put it here. 0.0 or 0.455910018. Then now you have h by 1 prime. So which means it is this one by 0.1. Okay, let's check what we're going to get out of this. Okay, then we're going to get 0.045591000189. Okay. So that's what we're going to record here. 0.0455. We've seen it on the calculator. 910018. Okay, then we have the next one, which is exactly what we're going to put. So now we continue, we finish this off with xn. That's what we have, xn. Then obviously the next one becomes a y sub n. Right, so with the y sub n, you would have yn primed. Hyn. One point. One four. Two. 9864. And then the yn primed. Not 0.52. 52. Okay, I'm just filling this in because they've been obtained in the same manner that we've been getting the rest of the values. And then we have 87. Then we multiply this one by 0.1. We actually are able to get out of the 87 by the h 0.05. 2525 6687. Okay. So now let us deal with these ones and deal with the next value. To get the next value, we said you add this and this, you get the next value, because this is a mastery discussion on the Euler method. So now it is expected that as one of our learning objectives, after this discussion, it is expected that any problem that is going to involve, say, just Euler method must be very, very easy. The presentation is yours. And okay, we're using the table now. It organizes everything, but you still can do without the table as well. Okay, see, in the first approach, I did not really stick to the table much, I'm sure. Okay, now let us have a summation of this one. So you add yn together with this to get that. So we're going to have calculator. Okay, so 1.14 2298 64. You add 0.05. 2 52. 5252, then 56687, which is 1.194 or 0.7 824309. 1.19482. Okay, then we're going to have the prime. This is y primed. So the prime becomes the following. How do you get yn primed in the table? You divide x by y, because this one is the yn prime to divide x by y. So we divide the x by the y to get this one. Divide the x by the y. One point 194 824309. 0.58 58601 928. 928. 928. Okay, so if you're dealing with this one at 0.7, you have 0.5858 601, according to what the table, the calculator showed us. Okay, then you multiply h by the prime. You multiply h by the prime with the calculator. Okay, so you have this one, but you multiply it by times 0.1. You have 0.0585860198. So you put it here. 0.05 858 60192. Okay, now then you get this one, to get this one, to get the bottom at 0.8, you need to, yeah, but like we said, this is n at 0, and then n equals 1 equals 2, n equals 5 for 0.5. So for 0.6 is n equals 6, n equals 7, n equals 8, n equals 9, n equals 10. So at 0.8, you would have the following. You'd have the following. So you're going to add yn and hyn prime to get the subsequent yn plus 1. So we have 1.19482 Yeah, you see, sometimes you might not really find a lot of the applications of octave, and obviously understand that the guy is interested in finding. But as said already, octave itself does not find it out, except that obviously we have systems to solve. And obviously the instruction is we can always solve the systems by using octave if the systems of equations arise. But not all problems have systems of equations, you see. And like this one, it doesn't have systems of equations. But when you add up, we have 1.253410328. So now that is 0.8. 1.2534. 1.2534. 10328. Then we have the primed. The yn primed is x over y. So you're going to have x over y. Right. So the minute we then have x over y, what is the x? The x is 0.8. The y is 1.2534. 10328. 0. At 0.8. So that's going to be 0.638258662. 0. Yeah, that is going to be at 0.8. Six, 3, 8, 2. 5, 8. 662. We'll continue. We continue. So now we're going to multiply this one by 0.1. Okay, we're going to multiply by 0.1. Let's see what we get when we multiply by 0.1. Okay, here we're going to take this value yn prime and multiply by 0.1, so times 0.1. 0.063825866629. So that is what we have. 0.06 3825, etc., etc. Okay. So which is 0.06 382 58 662. 0.06 38 258 662. Okay, now we're going to look at 0.9. So continue. We continue. Now, yeah, at n equals 9. Okay, we add these together with these together, values that must be put here. So yn plus hyn primed is going to give us a yn plus 1, which is the next. So a y8 together with h y8 primed is going to give us a y at 9, a y9. So now let us find the y9. So to get y9, the table just simplifies the calculation a little bit so that we have some procedural fluency. And what then we're able to achieve would be, we're going to have the top 1.253328. We add to 0.0638. 25, 8, 662, 1.317236194. 31723 7236194. So now in this case, you then divide the x by the y. Note 0.9, 1.31, 72, 36194. Continue, which is 0.68. Okay, so we have 0.6832487629. That corresponds to with the 9, the value at 9, 0.6832487629. So we're going to put it here. 683248.762 times 0.1. Not point that, 0.0683248.7629. Not 0.0683248.762. Okay, we continue, please. We continue with this method. At 10, how to get the y10? We add y9, yn at 9, but also the h y9 primed, we add them together. Because we add, according to the simple Euler, y to get yn plus 1, the next y, we add yn together with h yn primed. So now let's use a calculator. So now we're going to add 1.3172 36194. Not 0.06823248.762, which is 1.38556.107. 1.38, 1.3855, 6107. 107. One zero seven. So continue. Okay. So now what does it mean? It means two things, but it means therefore the wired one is approximately 1.3855 6107. Wired one is the square root of 2, which is approximately which is 1.412135562. We compare. Okay, so let us pause to compare these results. Let us pause to compare these results. Okay, this one is 1.414. Right, so let me just see if I can remove this. Right, so we'd have the 1.41421 3562. Okay. Let us compare the numerical solution we've got with the analytical solution of this particular solution to the differential equation. Let us talk about the exact solution. The exact solution is the square root of 2, which is approximately 1.414. 213 562. Then we're going to compute the error. Okay, we're just mastering the Euler method, please. That is what this is about. Normally, in the first question of the exam, it is either the Euler method or the Taylor or both in the first question. So it's very important. Obviously, one is just very aware of the Euler method because it appears normally it features in the first question, but I mean it can be in the middle of the exam, like when you're doing the shooting method, we use the Euler method as well. So now you'd have the Euler with H equals 0.1. Okay, we've got the value, which is this one. So wide one is 1.38556107. So you can actually put it here. 1.3855 6107. So now you get the error. The error is therefore the difference between the two. So if you get the difference between the two, then you'd have exactly the following. You'd have square root of 2 minus the value we've got, minus this one, which is 1.38. 5 6107. Okay, so getting 0.02865 up to 49237. Not to 865, not 0.02865 to 492. Right, so we have that. Okay, I mean, it is in comparison with Euler. There's something I want to discuss here. We did first the Euler with 0.2 and we got 1.35, 504, 1, 496. And then the error we got, just did the one of 0.2. The error was 0.05, 91, 72, 066. Okay, I want us to discuss the effect of the relationship, the actual difference between the H equals 0.1, 0.2, the effect on the accuracy of the solution in the approximation process, but also the error, which error is bigger, which error is smaller, when H equals 0.1, H equals 0.2, the comparison of the results. We note that. We note that having the step size from H equals 0.2. We started with 0.2, but now here we use 0.1. To H equals 0.1, what effect has this had? Has halved the error. But what is this? This is expected. This is as expected. Since the global error in the Euler method is H equals big O of H. Okay, we'll discuss the, yeah, we spoke about the big O of H last time, the odd. That is not normally used in the applications of those methods like your Adams-Moulton we spoke about last time. So now the big O of H, that is proportional. Proportional to H. Note that having the step size from H equals 0.2 to H equals 0.1 has halved the error. This is as expected. Okay, yeah, how true is this claim? That when we halved 0.2, we changed 0.2, we started 0.2, and then we halved it to 0.1. But now we're claiming that it has halved the error because the error at 0.2 was 0.06. 0.06. 0.03. So you can see, therefore, it is true that halving the step size from h equals 0.2 to 0.1 has halved the error. It has halved the error. This is as expected, since the global error in the Euler method is big O of h, that is proportional to h. Big O of h, that is proportional to h. That is proportional to h. That is proportional to h. Okay, yeah, we are saying therefore halving these the step size from 0.2 to 0.1, it has had the effect of halving the error. And when the error is halved, it is therefore evident that which method, which step is more accurate then. So in other words, the smaller the h, the smaller the error. If you halve the h, you halve the error. And in other words, you get results that are more accurate. But also at h equals 0.2, our approximate result is 1.355. And then now at 0.1, it is 1.38556107. And therefore, at this point, you can see that we are closer to the accurate result. The accurate result from the analytical solution is 1.4. Okay, at 0.2, we have 1.35. And then this is 1.38. 3835. 38 is closer to 1.4, meaning therefore that when we halve the h, the smaller the h, the more accurate is the result. The more accurate is the result. Right. The more accurate is the result. Okay, so this is something you need to take note of and make sure that you obviously are able to understand and be able to take note of. Right. We shall continue to think about these things, but I decided that today we have more focus on a method that is easy but important that comes in the exam. Either in the exam they give you the simple Euler or they give you the Taylor in the first question. In one of our previous discussions, we spoke about the modified Euler. It is the cousin. It is the cousin of this method because that modified Euler is the cousin of the Euler method. It is a refinement, it is an improvement of this, because the Euler method is okay, but the truth is it's not as efficient, it's not as accurate. Obviously, we can see the accurate answer is 1.414. But with this Euler, we're getting 1.38. It's not exact. So the mathematicians have been, how can we get an exact method? Because most of these problems sometimes is not possible to even get analytical solutions because these differential equations are difficult to solve. So if they're difficult to solve, then we ask ourselves, how best can we have numerical methods that are more accurate and more efficient to allow us to get more accurate results? So that becomes really our desire. Think about this simple Euler method and make sure you master it through this exercise. This is the mastery exercise to make sure that this method is given so much mastery, and one gets to master it, and one gets to look at exactly the mechanics behind it, how this method is applied, how this method is to be understood, and so on and so forth. Right, so that is food for thought. That certainly becomes food for thought. Right, so now here's a little exercise. Here's a little exercise. So this one is a home activity. Okay, this one is certainly a home. It's a home activity. It's a home activity. Right, so now this home activity is a home activity that you'll try. You don't need to copy it down because we're gonna send you the recording during the course of the evening. And then this problem you will try, but as said already, there are two methods that are cousins of each other. The Taylor series expansion. Solve the differential equation below by means of the Taylor series. We have spent time on the Taylor series expansion. See if you can use terms up to x to the power 6 delta x equals this. See if you can apply your knowledge of the series and the fact that the Taylor series is more general. The modified Euler is Taylor of order 1. Taylor of order 1. Okay, Taylor series expansion of order 1 is called Euler. It's called the Euler method. Okay, yeah. This is your homework. You're gonna try this, and you realize that obviously we're gonna send you the solution to this problem as well. The homework. We're just calling it a home activity for you to try, but we're gonna send you the solution as well, so that you can compare, and see how well you have managed to get this Taylor series expansion. Right. Keep us posted of your questions and so on. We'll talk more, please, on WhatsApp. I'm sure we'll look at what more we can share.
Okay, thank you so much.
Yeah, thank you so much. We keep in touch. We'll keep you posted. The recording is coming. Yeah, just try this home activity and see if you can be able to do it. Right. Thank you for today. We keep in touch, and yeah, we'll talk more. Okay.
All right. Thank you so much.
Thanks, dear. Have a good day and God bless.
You too.
Okay.
Bye.
Thanks. Goodbye.